Hello everyone. This is Abhijit Bishas, lecturer, Department of EEE, Brac University. I hope you all are doing fine. Welcome to this lecture. In previous classes, you have learned about different circuit topologies and design rules. So I hope now you can design circuits for a specific output. And when you design a circuit, then what will you do? You need to make the real device. So how to do that? In today's lecture, I will discuss that. This topic is called fabrication technology or fabrication. In today's lecture, I will give you an example of a very simple inverter circuit, how to make an inverter circuit in semiconductor level. So in CMOS technology, we fabricate the CMOS transistors or other transistors on silicon wafer. Then we have different steps. I will discuss this one by one later. And we have another. We have a special process or technique that is called lithography. I will discuss it later. It is just similar as a printing press. In every step, we deposit or etch materials, and after this we will have the final device. So let's see. Here we have an inverter cross section. So I hope you can recognize this. First, look at the picture here. This part, what we have here, this part is an NMOS, and this part is a PMOS. If you can recognize this, I hope you can also understand in this NMOS, this N plus region is the drain and this N plus region is the source. And for this PMOS, this is the source region and this is the drain region. And this is the gate, and this is the gate here. As you can see, we normally we can normally connect the VDD to the source terminal of this PMOS. Then we have drain, another drain, source, then ground, and this gate of NMOS and gate of PMOS, these are connected to the input terminal, that is A, and the drain of this both terminal, that is this and this, is the output Y. So I think you can understand this is a CMOS inverter. We have one PMOS and one NMOS connected in series. For fabricating N-type MOS or NMOS, we need P-type substrate that we have here, and for PMOS we need N-well or N-type doped body. So as we start with P-type substrate, we make an N-well here. So I will discuss it later how it is done. Here we can see we have a chart of symbols. What does these different symbols mean? Here we have silicon dioxide, N plus diffusion, P plus diffusion, polysilicon, and metal one. And you can see all this here. Well, before I go to in detail steps, let's see one more thing. Here what we have done, the substrate, this P-type substrate should be connected to the ground, and this N-well should be connected to the VDD. I hope that you, if you have done in simulations in the software given, you know the N-well must be connected to the VDD, and this P substrate should be connected to the ground. I will discuss the reasons for connecting the N-well in with VDD and substrate with ground later. So to connect this P substrate, with ground, we need a good contact. If we just use this metal, if we just put a metal in P substrate, that will not be a good contact, because this P substrate is not heavily doped. This is very lightly doped. So lightly doped semiconductor normally does not make a good contact with metals. So we need another doping here, that is P plus, that means heavily doped P region, and then we connect it with the metal. And for N well, we have heavily doped N region here that will connect with the metal, and these are called substrate contacts or taps. Okay, here we have inverter mask set. The term mask is a basic term here. Whatever we will have here or discuss here, say it can be polysilicon or the N-type doping, P-type doping, VDA grounds. This everyone will be one mask. Just a terminology we use here, mask. And okay, as you can see this, I hope you can understand. Okay, let me draw. I hope you will recognize this as a PMOS, as CMOS inverter circuit. From this we get the output, and these two gate terminals we give the input here. In this picture you see this is the source region of NMOS, this is the drain region of NMOS, this is the drain region of PMOS, and this is the source region of PMOS, and this is the taps that we use to connect NOL with VTD and P-type substrate with ground. We can show it in this symbol here, but we will not. Okay, let's see. So here we have a detailed mask views. That means what we have used. We have used NOLs, polysilicon, N plus diffusions, P plus diffusion, contacts, and metals. So these all comes one by one, one after one. So fabrication are done in huge factories. These are called Fabs, and they are clean rooms, very large clean rooms. Clean rooms are normally cleaner many more than 1,000 times than a normal environment, so that no dust particle can enter into the IC or the device. We start the fabrication steps with a P-type silicon material, silicon disc actually, that is called wafer. At first we will make a NOL here. To make a NOL, we have to dope this region with N-type dopant. Before I dope this region, I need to cover the rest of the surface so that only the desired region is doped with N-type dopant. Normally we use oxide layers to cover these areas. I'll show how we do it. At first we grow oxide layers above this P-type substrate. Then okay, the method I am going to discuss now, this is called lithography, and for our case, especially this case, we are using photolithography. Above this oxide layer, we put a layer of photoresist. What is photoresist? Photoresist is a light sensitive material that softens when exposed to light. So we will expose this region where we want to make the NOL to the light. so that photoresist softens here, and we can easily remove it. So after removing the photoresist from this region, we have this structure here. After this, we will etch the oxide layer from this region. So we have this structure here. Initially, we wanted to cover the region we don't want to dope, so we have done that with this oxide layer. Now we don't need this photoresist layer here, so we remove that also, and finally we get our desired structure. Now we dope here and make a N well in this region. There are two methods for doping. First, diffusion. In this case, we place the wafer in a furnace with arsenic gas, and the arsenic atoms diffuse into the exposed silicon. Another method is ion implantation. In this case, the open silicon surface is bombarded with arsenic ions, and the region becomes N-type. Normally, most of the cases, ion implantation method is used. During the doping, this oxide layer protected the rest of the wafer, but after creating this N well, we don't need this oxide layer anymore. So now we strip off this oxide layer, and we have this N well in p-type substrate. In the next step, we will make the gate part for the MOSFETs. First, we grow a thin layer of thin gate oxide layer above this substrate. Then we deposit polysilicon. Here we use chemical vapor deposition, that is CVD method, for depositing polysilicon. There is some other ways to deposit materials. The methods that will be used depends on what material I am going to deposit here. Now we actually don't need this polysilicon and oxide layer all over the substrate, but we only need this in these regions where we will make the gate. So again, using the lithography technique, we make oxide layers in these regions. Then we strip off these portions, and after that we also remove these oxide layers. So finally what we will have here, this we have polysilicon that will work as metal. Then we have oxide here, and then the semiconductor. So we have MOS structure here and here. This will be NMOS and this will be PMOS. So here we actually have two views. If we see from the above, okay, let me draw first. See, here we have a 3D structure of this IC. Now if we have a shape here, that is U-shaped, and we take a cross section along this line and look at that cross section, we will see this picture. But if we see from the above, we will see this picture. So these two pictures are given for better understanding, and this dot is a line, dotted line is this cross section line. After this, we will make the source and drain region for the MOSFETs. First, we will do N-type doping, that will create a source and drain of NMOS and N-oil contact. To do this, First, we cover the whole surface with oxide layer. Then we use that lithography method to expose those regions where I want to dope. Here, these regions are exposed for doping. One more thing, the oxide from above the polysilicon layer is also removed. In this self-aligned process, this polysilicon protects the region below it from the doping. After completing the doping, we will have this structure, and again we don't need this oxide layer now. So after removing that, we have this. Now again we need to create the source and drain region for this PMOS here, and here we need the tap. So we follow the same procedure as before to make these regions. So finally we have this structure. After this we need to make contacts. Again we first cover the whole surface with the oxide layer, then expose the regions where we need to make the contacts. To make the contacts, first in most of the cases, first a thin layer of titanium is deposited in these places, because titanium has a very low resistance and a very good adhesive property. It works as a glue between the metal that will be deposited here and the semiconductor material here. After making the contacts, we need to put the metals at these contacts. This is called metallization, and normally aluminum is used for this purpose. And these metals are used for connection with the external circuits. I am almost at the end of this lecture, but before I finish, I want to discuss some more topics. First, consider this part here. We deposited the metal at this contact, and for this contact we used a titanium layer. If you have already used the software tool, you should know this metal layer, the first metal layer, is called M1, and this is a horizontal line, so I can call this part is M1. Normally the M1 doesn't have any vertical part. That means we cannot include this part with M1. So what is this? Okay, these parts are known as local interconnect. Normally you can use any material to fill these portions, but tungsten is preferred over other materials because it has ability to fill holes without leaving voids. So this is one thing. Then we have another topic to discuss. In this case, we have used a silicon wafer and fabricated our transistors on it. But the silicon wafer is normally a bulk substrate. For better performance, sometimes we grow a epitaxial layer above the bulk semiconductor and make our transistors in that epitaxial layer. Next, you can see we have a large separation between two transistors here. But when we are considering VLSI circuits and smaller and compact design, we cannot afford this much space between two transistors. So in that case, we use something called shallow trench isolation. We just put a oxide layer here after one transistor. Just after that, we can fabricate another transistor. After that, we have You can see in this design there are oxides. So you can see oxides here, 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 and here, and also here and here. So these two oxides are called the gate oxide, that is used in the gates of MOSFET, and all other oxides that is present here is called field oxide. Then we have another important topic. In your electronics course, you have seen MOSFETs. They are the metal oxide semiconductor. That means you had metal, then oxide, then semiconductor. But in this VLSI circuit, we are using polysilicon instead of MOS. Why? Have you ever thought about this? Okay, I'm telling the reason in short. In this process, first we had made the gate, and after that we have formed the diffusion layers. If we use metal, then not only in this case, in fabrication process, metals are deposited at the end, because after depositing any metal, especially aluminum, you cannot do any other step that requires high temperature. Normally for depositing these diffusion layers, after the diffusion you need high temperature processing. So if you use the metal, you have to make the gate part of the device at the end. But there is some problem. If you make the gate at the end, then you will have problem while you are making smaller devices. So we need to make the gate before the diffusion layer. To solve this problem, we use this polysilicon. As polysilicon is not metal, we can deposit it anytime, and this polysilicon, especially doped polysilicon, is good conductor. So this is why we are using the polysilicon in this case. Another thing I mentioned earlier, that we are using these taps here. The reason for it, there is a effect called latch up. To prevent that latch up, we use this connection. That means we connect the N well with the VDD and connect this E substrate with the ground. So that's all. But remember one thing, we have discussed a very simplified process here, but in real life there may be some other intermediate steps. So that's all. Thank you.